in chapter 4, I mean 2, we're dealing with fluid statics, right? Nothing was moving. You were calculating hydrostatic pressures, and the fluid is stationary. Now, chapter 3, we're going to learn about fluid dynamics, right? And that's one way to solve fluid dynamics problem is by using integral relation, which is Reynolds transport theorem. Once we jump into chapter 4, we learn a different tool called differential relation. So this one's dealing with integrals. That one is dealing with derivatives, right? Two ways to solve problems. Okay. So any questions from this one? You guys know, I know, Marissa, you said Reynolds transport theorem, right? That's the major thing in chapter 3. Transport theorem. And what's the general equation for this one? Should have like a general one for Reynolds transport theorem.
D dt of B of the system equals D dt of the integral over the control volume.
Yes, exactly.
Of beta rho dV.
And this dV is what?
The transient term.
Yes, this is the transient term, but I mean this V is velocity or volume?
Volume.
Yes, volume. Exactly. And
then plus the integral over the control surface of beta rho times the dot product of V V dot N times dA.
And what's V right here in this one?
It's the velocity, the
This
relative
is velocity.
velocity.
Exactly. Yep. Okay. And what's this N right here?
It's the vector that's normal to the area.
Yes, exactly. Is it called the direction vector? I forgot. But yeah, it's the vector normal to the area, surface area. Okay. And what else? You guys know what beta is in this term? What is beta?
Well, could it be like any parameter?
Exactly, yes. It can be any parameter. Yeah, beta can be any parameter. So in the book, the way they define beta is dB over dm. That's the definition of beta. And this b right here can be any parameter you choose. So what are the parameters we can choose?
Mass, energy.
Yes, mass. Beta or B can be mass. It can be energy. And what else? What else is conserved, right? Mass, conservation of mass, conservation of energy, and what else? We're missing one. Remember physics, what is it called now? I took physics 131. I'm not sure what is it called in semester system. Yeah. Well, yeah, what else we learned?
Momentum.
Yes, exactly. Momentum. Momentum is conserved. And this one can be linear momentum or it can be angular momentum. Okay. So conservation of mass, everybody agrees mass is conserved, right? What about energy? Is energy conserved?
Yes.
Yes. And which law of thermodynamics deals with this one? Conservation of energy, as or if you're taking thermo or you've already taken thermo. Remember? Refresh your.
Yeah, I don't remember.
Have you taken thermo before this class?
Yes, I did.
Okay. So if I ask you what's the first law of thermodynamics, how would you answer that one?
That is conservation of energy.
Conservation of energy. That's it. That's the only thing. It's just a different name, right?
Yes.
And the second law of thermodynamics is something else. But and momentum is conserved. We know that from physics 1, I believe. We learn about momentum. Okay, mass, energy, and momentum, and yeah, dynamics too. We learn about conservation of momentum, right? Yes, I think we learn about momentum and dynamics. Okay. So we said B can be equal to mass, so you can. This one can be mass, or it can be energy. You can plug in E. You can plug in M for mass. What about momentum? What do you plug in if you want to find the momentum? How would you calculate momentum?
NV for linear momentum.
Yes, for linear momentum, it's mv. It's just mass times velocity. And remember, we're plugging in beta in this equation. We're not plugging in b, right? So if I mark, so beta is here, and there is another beta here, and a beta right here. We said b can be m, energy can be E for B, and what about momentum? We said mv. So for this one, B is equal to mv for momentum. So beta, what is beta equal to? You guys know?
MVDM.
So it's going to be d mv, right, over dm. And what is that?
The change in momentum of the system.
Yes, but I mean, what beta? What's beta is going to equal to something. So you see right here, this b. Oh, I have no idea how that happened. But yeah, so b is equal to mv, right? That's momentum is equal to mv, mass times velocity. So if you plug in this b into this equation, you'll end up with this one. So dm over dm is 1. So beta is equal to velocity, really. So what do you plug in here in beta for momentum? You plug in velocity, and that's it. Are you guys confused? Did I confuse anyone? I think I drew so many arrows.
No, that makes sense.
Make sense?
Yeah.
Okay, so for mass, you plug in m, right? Or no? For transport theorem, this one, if you're solving for conservation of mass, what do you plug in for beta?
Just M.
Well, isn't it 0?
Guess again. You're close, but guess again. So what is beta? B is m, right? B is our parameter, m.
Just 1.
And beta is dm over dm. So you plug in 1.
Yes.
That's for mass. Mass. What about energy? B is equal to E. I should fix this really. So B, not beta, B is equal to E, energy. What is beta?
DE over DM.
Exactly. So what do we plug in for beta in this case? We just plug in E in this case. this is energy, and this is momentum. We said for momentum you plug in v, which is the velocity. Momentum plug in v, velocity. And that's it. So you want me to write the 3 equations for mass, energy, and momentum? So you can have them in your notes. Or I think the professor went over them in the video, no?
Yeah, he went over them.
Oh, okay. So you have the 3 equations, right? You don't have to keep deriving stuff in the quiz or midterm. You just have the 3 formulas and you follow them. Is that right? You have them in your notes?
I'm not sure if he's completed fully momentum. I think he's gonna go on to that tomorrow.
Tomorrow. Okay. Well, okay. So it's 12:15. Let's write down the 3 equations so you can have the mass. We said it's what? How would you write this transport theorem for mass?
It'd be the derivative of 1, which is 0.
Exactly. So 0 is going to be equal to d over dt, the integral of the control volume. Beta is 1. Remember, beta is 1 for mass. So density times dv, or the volume. This is the volume. And then the integral of the control surface. Beta is 1. Density times velocity times n, the direction vector, dA. And that's your law of conservation of mass, basically. And I think Nick highlighted a pretty good observation that this one right here is the transient term. And what do we mean by transient? You guys have
Sometimes
any
it'll,
idea?
yeah, sometimes it'll just be 0 if it's constant.
Yes, so sometimes the transient will be 0 when it's constant. Can you explain more? What do you mean when it's constant?
So when the density doesn't change,
Okay.
that's pretty much how I know.
Okay, let me ask this. What's the difference? What's the opposite of a transient system? Or what's the opposite of a transient?
Something that's changing.
The opposite of transient, something is changing? Transient means something is changing.
Steady flow.
Exactly, steady state. So the opposite of transient is steady. Okay, so and what do we mean by steady? You know, Marissa?
The volume doesn't change. The
Volume, yes, the volume doesn't change. With what? You need to mention this last piece of your explanation. It doesn't change with respect to time.
Okay, yeah.
Right?
Yeah.
So very important, because we have d over dt. So something is changing with respect to time. If you have something changing with respect to time, this is a transient system. Okay? But most applications in fluid mechanics and what we're dealing with in this course, I believe everything will be, mostly everything, 90% will be steady. Right? Nothing is changing with time. If you leave the system now and you come back to it 100 years from now, it will be the same. No reading will be changed. Like no readings will be changed. Everything is constant with respect to time. Okay, that's the definition of transient and steady. Okay.
So the opposite of transient is steady.
Yes.
Okay.
It is.
Thanks.
Yep. Transient means something is changing with respect to time. Steady means nothing is changing with respect to time. Okay. So if I have a pipe, let me ask you this. If I have a pipe and you have a flow inside this pipe, okay, and the velocity right here is equal to 5 meters per second, and the velocity right there is equal to, let's say, 7 meters per second. Is this a transient or a steady state system?
How would that be transient?
Okay, Nick is saying transient. Who else we have in chat? Marissa.
I think I'd also say that it's transient because the velocity isn't uniform. That's my reasoning for that.
Okay. And who else we have in chat? Participants. Oh, we have Alicia too. Are you you wanna take a guess?
I guess, yeah, maybe it's transient just because
transient
velocities changes based on, or yeah, it changes based on time.
It changes based on time. Okay. So let me ask this. If I leave this pipe, right, and come back to it 15 years from now, the velocity will be the same or has it been changed?
It would be the same.
Oh, you know what? Yeah, you know what? Wouldn't this be a steady flow then?
Exactly. It will be a steady flow. Yep. Even, I mean, yes, the velocity is different in each location, but it doesn't mean it's transient, right? It doesn't mean it's transient. Transient means it changes with respect to time. Nothing is changing here with respect to time. The value is not constant, it's not uniform, but it's not changing with respect to time. That's why it's steady, it's not transient. Okay. Right? If I write this thing, oh, I think it disconnected. Okay, let me just share my screen really quick. Okay, so if I write this one is equal to v, and the velocity here is equal to 5t, t being time, and velocity here is equal to 7t squared. Is this a transient or a steady state system?
That's transient.
Why?
Because it changes with respect to time.
To time, exactly. If you plug in seconds, let's say I come back after 10 seconds, now the velocity is 50 at the top. If I come back at 30 seconds, now you have 150 at the top. So anything that changes with time, you have a transient system. Okay, good explanation.
Yeah, thanks for that clarification, because with respect to time is very helpful.
Yes, yep. I remember when I took this class too. It's just, that's how my professor really answered my question, because I had this question about, I thought it's transient, so don't feel bad if you like answer it's transient. Of course you're gonna say it's transient, right? The velocity is not the same, right? But the professor showed me this example, and now yes, I know what's the difference between transient and steady state.
So I guess if the velocity is constant and there's no acceleration, it would just be steady?
Yes.
Basically? Okay.
Yep.
Thank you.
Yep. That's if it's nothing is changing with time, you have a steady state system, and most like the app, like what we're doing right here in this class, more like everything will be steady state most of the time. Most of the time, I'm saying, because some problems will deal with transient state. Okay, good. Should I move on? Good explanation on this one. I know it's not really relevant in this chapter, but I think once you jump into pumps, when we learn about pumps, right? And yeah, you have a transient and you have steady state, right? So I think this is like a pretty helpful example to differentiate between the two.
Yeah, definitely.
Okay. But yeah, I think the book mentioned, I was reading the book on Tuesday, and it mentions, yeah, most equipments like pumps, boilers, condensers, right? You're going to learn about all these things in thermal fluids, which is the next class after this. You're going to learn about power plants, which is what I'm studying right now. Power plants and energy systems. Everything we consider is steady, really, right? Yeah, so it's a good assumption. It's a good assumption to assume it's steady. Okay.
Okay.
So let's see an example, right? Enough with all this theory. Let's. You guys want to see examples?
Sure.
Oh, I left my papers there. Okay, so I have an example from chapter 3. Okay, so I have a problem. I'm not going to jump in. I think chapter 3 deals with Bernoulli's equation too, right? Did the professor say anything about that one?
I don't recall him mentioning
No.
that.
Okay, no Bernoulli's equation. Okay, I forgot about that one. Bernoulli's equation is the most important thing in fluid mechanics. So yes, once you guys, I think I'll watch the video on Friday when the professor posts it. But I think he will deal with it will deal with Bernoulli's equation. It's a really powerful one. Okay, but for now, yeah, let's use this Reynolds transport theorem for a problem. Let's see how we apply this thing. Problem 3.12, and you have, let me draw the problem. So if you have the book, you can go to problem 3.12, and you kind of see this problem. It's like a tank that is attached to a pipe, and the velocity here is 2.5 meters per second, and velocity at the exit of the pipe, v2, is equal to 1.9 meters per second. And what else? We have the diameter of the pipe. This is the diameter of the pipe. It's 12 centimeters. And you have the height of the tank is 1 meter. And the not the radius, the diameter of this, it's a cylinder. And it's open to the atmosphere. The diameter is 0.75. meters, and we're asked to find the time to fill up the tank. Time to fill up the tank. And given that the depth of this of water at the start is 30 centimeters, and I know this is not to scale, right? This is definitely not 30 centimeters. Okay, so let me extend this one. So at the start, we have 30 centimeters of water, and we're asked to find, okay, how long will it take to fill up the entire tank? Is it a clear picture? You guys can see this, or is it?
That's fine.
I know. Okay. I mean, always look at the book. Much more better. Okay, so what do you think? Let's see. What do you think? How would you solve this?
Start off by determining what parameter we're going to be looking at.
Yes, exactly. Yep. So what parameter we'll be looking at right here? We're asked to find the time to fill up the tank.
I want to say mass.
Yeah, mass. Definitely not energy, right? I mean, it should be obvious. It's not energy. It can be momentum, right? Because the momentum has mass, but momentum we only. I think I should say that we only use momentum when we're dealing with forces, right? I think I didn't mention this here. I know mass, if you do the transport theorem for mass, it's 0, right? What about momentum? How would you write the momentum equation? Let's do this before we jump into the problem. Okay, you guys have the equation for momentum, or should I write it down?
I don't think we have the equation. Wait, maybe we do.
Yeah, you can double check.
Oh yeah, we do the sum of forces.
Yes, very important. The sum of forces is equal to
d dt.
d dt.
The integral of the control volume.
Okay.
Times, velocity rho dv plus the integral of the control surface velocity rho. Wait, I'm not sure if that one's velocity. I didn't know that.
It is velocity.
Okay.
Yeah.
Times the dot product of relative velocity and the normal vector.
Yep.
dA.
Let me scratch this. dA. So that's your momentum equation. That's your mass equation, and that's your momentum. Okay, so you have at the left side of the equation, or at the left term, is summation of forces. So it should be easy to identify any problem that deals with forces. You're probably going to be using momentum. So in this case, we're not dealing with any forces. We're just dealing with volumes and heights and these things. So that's why we're using mass. And I didn't use energy because I don't see any heat. I don't see any work. I don't see any power. I don't see a pump. There is no boiler, no condenser, nothing. That's why I used mass. Very simple. Okay, good. Should I give you time to solve it, or you guys want me to go over it? It's up to you.
Can we go through it together?
Okay, sure. So you want to apply this formula right here, right? You want to apply this formula?
Yeah.
This one, right? Okay. So we know it's 0, and that's going to be equal to d over dt This is rho d volume plus, oh, this is control volume, this is control surface, then you have density, you have velocity times n, direction vector times dA. Okay? And this problem is what?
It's a steady flow, right?
Yes,
I mean,
exactly.
steady state. Steady state. Is that the right way to say it? You don't say steady flow, you say steady state?
Okay, a steady flow, you need the steady state to have a steady flow, right? But steady flow is something else really in fluid mechanics. It's when the velocity has a parabolic shape in a pipe. So yeah, I mean, we still did not learn about that, I think. I think that's in later chapters. But yes, it is called steady state, right? And a steady flow is reached when you have a steady state.
Okay.
Okay. Okay, so you have exactly, you have a steady state problem. I don't see anything changing with time. Do you see anything changing with time in this problem?
Or could we say that the volume is changing with time because that's the whole problem. We're trying to see when it fills up.
Exactly. So there is something that is changing with time, which is the height of this water in the tank, right? Or you can say the volume, because it's a 3D problem. So the volume is changing.
Yeah.
Right? Okay. So where would you draw your control volume? You need to, in statics, we learned how to draw a free body diagram. In fluid mechanics, you need to draw a control volume.
Just around the tank.
Around the tank. Okay. So let's use a blue pen. So you're saying this is your control volume?
Yep.
Okay.
I think it needs to go further down. That way velocity, we can incorporate those given velocities.
So what's your inlet in this case? You have this tubing that connects the tank to the pipe. This is your inlet, right?
Yeah, the inlet would be...
Inlet here. This is your inlet. But what about this? What about if I draw the control volume like that? This is my control volume. I have an outlet here. This is my outlet. This is my outlet. And this is my inlet. Is that even better?
Oh, so we can figure out how much is actually going into the tank?
Yes, you can do that. Yep. And then use, after you figure out how much there is water or how much mass coming into the tank, you can basically find the height easily. So it's all about drawing your control volume. And this is a good one because we have the inlet, we know the inlet is 2.5 meters per second. We know one of the outlets is 1.9. So we can solve for the other outlet, which is the tank.
So the previous control volume that I think Nick suggested, would we have been able to solve that or no, because we don't know the velocity at that inlet?
You wouldn't be able to solve it. You would need to split it into two control volumes, like this one, and you can draw another one on top. But it's
That's
really,
what I was thinking.
yeah. So if you, okay, let me ask this. If you draw the control volume like this, you have an outlet and you have an inlet. Is this a good control volume?
That's kind of confusing.
It is not a good control volume because this tank is inside the control volume now, And anything that's happening inside the control volume, we disregard, right? Like in statics. It depends how you draw your free body diagram, right? We don't care about the water coming in here because it's inside the control volume. Anything happens inside the control volume, we neglect. So this is actually a bad control volume. That's why this one, what Nick said is good, but it's not sufficient, right? If you draw your control volume like this around the tank, right? We don't know the inlet. We don't know the inlet, so that's a problem. That's why it's better to draw the control volume like this. That's your control volume. Let me zoom in. That's your control volume. You have velocity coming in, velocity coming out, and you can solve for this one coming out of the control volume.
Okay, that makes more sense now.
Mm-hmm. And basically, once you find we're basically finding the velocity here. Okay, once we find that, you can use, how would I say this? Once you know the velocity, how much water coming into your tank, you can just do algebra and find the time, right? It's basically not fluid mechanics anymore. Fluid mechanics ends when you draw this control volume. That's it. Okay. So let's see. So we said it's a steady state, right? Because the velocity is constant. You have 2.5. You have 2.5 coming into your control volume, 1.9 leaving your control volume, and you have still an unknown velocity going into the tank. And these will not change with time. These will be constant, whether the tank is completely filled, it's overfilled. It doesn't matter. The velocities will be the same. That's why it's steady state. So we can cancel which term if we have a steady state problem?
First term.
First term, which is the transient. We can cancel this one. And let's analyze this one, this term. So you have 0 is equal to what? And remember, you have to write this for each inlet and outlet. So we have one inlet and 2 outlets.
The sum of rho.
The sum, okay, the sum of rho.
Rho I VI minus the same thing.
So rho times velocity.
The area.
Inlet.
Yes.
Times the area. Right?
Right.
Okay. And what else?
Minus the same thing, but for the outlet.
V outlet times area. And why is it minus? How did you know it's minus?
Because it's going out.
It's going out. It's leaving the control volume. Okay. And what does that mean?
Or my bad. Shouldn't it be the other way? Because of V dot N would be negative for the inlet.
Okay.
Because,
so yes, very good. Yes, exactly. So N, remember, N is always facing outwards, right? So here's your N. N, N, and N. Right? So for the inlet, the velocity is coming in and N is facing outward. You have a negative value. Okay. So here's negative. It really doesn't matter because the other one will be positive, but it's nice to follow a convention, right? Our answer will not be changed, right? Because this term will be negative and the other one will be positive, and it's really the same. It's just it's nice to follow a convention. Okay, but yeah, and what about the outlets? The velocity of the outlet is facing,
It's in the same direction as the
it's in the
normal vector.
same direction, exactly. So this one should be positive. Questions? So this n vector, or this normal vector, this is what makes a term positive or negative. If it's facing velocity like this one for the outlet, it's positive. If it's going the opposite way of the velocity like this one, it's negative. That's why we have a negative sign, an inlet, and positive sign for outlet. It's just nice to follow convention, really. That's it. Okay. Are we good?
Yep.
Yeah.
Okay. So let's do this. How would you solve this? How many inlets you have?
Just, we have one.
One. So you can rewrite this as density V1A. 1. Let's call it A1. What about outlets?
We have two
One.
outlets, right?
You have 2 outlets.
Oh, my bad.
You have 2 outlets, exactly. That's how we drew our control volume. We have an outlet through the pipe and to the tank. So density times V2, A2. This is negative. Should be negative here, and this is 0. Okay, we said the summation of all the outlets. So this is the first outlet, which is this one. Okay, what about the second one? This outlet.
It would just say rho V3A3 plus rho V3A3.
Yep. Yes, that's exactly how you should write it. Very good. And now, what do we do? Can we simplify this problem? What's a common term you see in these, like in this equation? Rho, right? Density is a common term. We're dealing, I think, with water in this problem. And water is called an incompressible fluid. So density does not change, really. So if density does not change, you can cancel it. Cancel this term. Let me use, yeah, and cancel this term and cancel that term. Should be using red. Cancel this, cancel that. Yep. So now you're left with what? V1A1 is equal to V2A2 plus V3A3. Good. I just moved V1A1 to the other side.
Yeah.
Okay. And does this remind you of anything, really? What does this equation mean? Let's analyze it. So V1A1 is Q, is volumetric flow rate. So this is Q1. V2A2 is what?
Q2.
Q2. And V3A3 is Q3. Okay. And what is Q? Q has a unit of meter cubed per second. Volumetric flow rate, right? And what's the equation for it? It's basically the velocity times the inlet area or the outlet area. Mass flow rate, which is kilogram per second, has this equation, density times VA. So if we left densities, we're dealing with mass flow rates. If we factor out the density, we're dealing with volumetric flow rate. Okay. Good.
So that last one is mass flow rate.
This one is mass flow rate. This one is volumetric flow rate. Velocity times area is volumetric flow rate. Density times, or basically density times volumetric flow rate equals mass flow rate.
Okay. Thanks.
Okay. Yep. And this should remind you of circuits, right? If I mean, I personally don't like anything that deals with electrical engineering, but I mean, yes, this does remind me of circuits, current, right? Whatever is coming into your system, it should go out. Whatever is coming in, 1, it should go out. You have 2 and 3, right? Can you visualize this by looking at the
Yeah.
problem? Whatever is coming in, it should go out, right? And why it's not going out at the same velocity? Because the area is different. If the area is the same for all 3, velocity will be the same, and the problem is solved. But because we have different areas for the tubing and the pipe, that's what changes the volumetric flow rate. It's the area. I mean, that's not what changes the volumetric. That's what changes the velocity. It's the area. Right? If you have a hose with the water coming out, if you like try to press down on the hose, you'll see water coming out very like faster, because volumetric flow rate should be constant. So if you change the area, velocity will be faster to keep Q constant. That's how I look at these problems.
Yeah, that makes sense.
Yeah.
Yep. Because Q should be constant at all times. This is a steady state problem. No accumulation, nothing in the system. Okay, good. So you can solve for this one. You can plug in values, really. Plug in values. If you plug in values for V, we know V1, we know A1, we know V2, we know A2. It's the same pipe, same diameter, 12 centimeters. Do we know A3? This area of the pipe or the tubing here?
No.
No, the problem did not mention. So it's best to leave V3, A3 as Q3 and solve for Q3. Okay. So Q3 is equal to a value. Did I lose you guys? Are you guys lost, or is it okay?
I'm kind of confused right now because we're not done solving it, right? Q3
No.
isn't the answer.
No,
Okay.
Q3 is not the answer. So once you find Q3, but you know how we got to Q3.
Yeah.
Do you understand that part? Okay, perfect. So you can manipulate V3 A3 is the same as Q3. You can just manipulate the formula. And this one is 0.00679. What's the units for volumetric flow rate? Meter cubed per second. Okay. Now we know the volumetric flow rate going into the tank. How do we calculate the time it takes to fill up the entire tank?
We'd have to calculate the volume of like space that's left in the tank.
Exactly. So
Multiply
the
that.
volume of the tank.
Is this like a rectangle like container or?
No, this is a cylinder. So you have pi
okay.
over 4 times the diameter squared. That's the area times the height, h. Now you have volume. This is the equation for volume of a cylinder. So if you plug in the values, pi over 4, diameter is 0.75 squared, times height is 30 centimeters, I think. Yes, we need to fill up 70 centimeters because 30 centimeters is already there. We need to fill up the entire tank, 1 meter. So what should I plug in?
0.7 meters.
Yes, 0.7. I shouldn't plug in 1 because we already have 30 centimeters. I know I went over time a little. Can I finish this problem, or you guys want to see this next session?
I'm okay with finishing. I think we're almost
Okay,
done.
it should take us 3 minutes. That's it. Pi over 4. I'm just doing the calculation to find the volume. Okay, so it is 0.3093 meters cubed, right? The units for volume. The unit for volume is meter cubed. And what else now? So I know you said something, Marissa. How would you find now the time? You have the volume, and you have volumetric flow rate. How would you find time now?
You divide it by Q.
You divide it by Q. Exactly. Yes. You solved it based on units, right? Or how did you think about it? Just common sense, or you solved it by units?
Well, the volume is meters cubed, and then Q is meters cubed over seconds. So the meters cubed goes away and seconds goes to the top.
Exactly. Yes. So you looked at units. Very good. Yes. That's the goal of this class. Just looking at units. Okay. So yes, it is actually T is equal to Q3 over volume over Q3. Sorry. Yes. Volume over Q3. Right? We know the volume. We know Q3. 0.3093. And this is 0.00679. This is meter cubed per second, and this is meter cubed. And like Nick said, once you do the division, you'll end up with basically seconds, which is your unit for time. And it should roughly take, let's see. It should roughly take 45.55 seconds. Good?
Yeah, I feel like I would have made definitely some errors along the way. So I'm glad we went through this together.
Okay. I mean, did you attempt this problem? Is this from the homework?
I actually haven't tried any problems, and he hasn't
Oh.
assigned them until tomorrow.
Oh, okay.
Yeah, he hasn't assigned any homework yet.
Any homework? Okay. Hopefully I'm like at the same pace as the professor. Did I do anything that the professor did not
No,
explain?
you're fine.
Okay.
No, it makes sense. Yeah.
Okay. Okay. That's why I don't want to deal with momentum, because you said professor did not deal with momentum. So let's wait. I think but this is a good problem, right? Yeah. Any questions about this one?
No, thank you.
No questions? Okay. And remember, if you're not in the Discord channel, you can leave your Discord username in chat and I can add you to the server.
Oh yeah. Have you posted the videos?
No, honestly not yet, no. But I have them and I should post them tonight. It's basically all these recordings we're doing. Okay, any questions, guys? Do I go too much over theory? I don't want to do that, right? I want to solve as many problems as I can, not going over theories.
No, to be honest, at first I was like, okay, I get this, but I mean, we touched up on transient and stuff like that, so that I I had questions on that, and I think that really helped today.
Okay. Yeah, sometimes I like to see some theory, right? I don't like to see some derivations and stuff, but I like to see some theory before I jump into the problems, right? It just helps me. Okay, questions you can ask, you can email me. You guys know my email?
I don't know it.
I mean, you can type it in CPP email. Just my first name and last name, it should pop up. But here's my email. Post it in chat.
Cool, thanks.
Okay, any questions? And pretty sure Professor has office hours too. So you can ask him. And you can ask me. And if you want to be in the Discord server, that's even better.
I have a question.
Yeah.
How do I find out my username on Discord?
Oh, your username on Discord.
Like, where do I go to see it?
You just go
Honestly,
down to the bottom right.
Bottom right?
So when you click on the app and then
Yeah.
you click on, so I'm guessing you'll probably like, when you click on the app, you'll probably end up in like a group chat that says like hashtag general hashtag. It could be
Yeah.
anything. And then
Yeah.
in the upper left corner, there's like the 3 bars. And then if you click on that, it'll like display a bunch of stuff. And if you go down to the bottom right, there's like an icon, and then you just press that. And then there's like a little thumbnail thing, and then under that it should have like your username.
I'm on my laptop, so I think it's slightly different.
Oh, okay, yeah. I'm on my phone.
and did you send any messages to anyone on Discord? Just go to
Did
the
I?
chat. No, did Marissa.
Oh, okay, yeah, I did.
Go to the chat and click on your name. It
Yeah,
should give you your
do that
name
one too.
and a hashtag.
Okay, so it's the name and hashtag together.
Yes, I
Yeah.
think so. Right,
So
Nick?
the number.
Yeah.
Okay.
Okay, because I'm not good at adding people. I don't know how to add people on Discord. It's just I use it too much, but I don't know how to add people.
Okay, I sent my username then.
Okay, let me write it down. Okay, I can add you later, but hopefully tonight I'll post all the videos and stuff tonight. And
Okay. Yeah.
I don't feel
Sounds
it's
good.
so active, this Discord, but you guys make sure you ask, right? If you have any questions, just ask.
Okay, well, I'll see you guys next week then.
Okay, all right.
you.
Take care.
You too.
All right. Thank
Bye.
you.
Thank you.